Scene 1, the Amplitude Paradox. Welcome to the 14th lecture of our wave mechanics series. Today, we confront one of the most counterintuitive paradoxes in electromagnetics, a phenomenon that has deeply confused many mainstream material scientists and exposed a fundamental misunderstanding of physics in top-tier SCI journals. If you look at the boundary interface of a microwave absorbing film or a thin film without a metal backing, you will notice something shocking. The amplitude of the transmitted beam, F1, can actually be larger than the amplitude of the incident beam, I. Under certain conditions, the amplitude of the reflected beam, R2, from the rear interface can also exceed the incident beam. To a casual observer, this seems to flatly violate the principle of energy conservation. How can a transmitted or reflected sub-beam carry more amplitude than the original beam that created it? Today, we will deconstruct the elegant physics that resolves this paradox and show how the absolute laws of energy conservation are perfectly maintained. Scene 2, the critical distinction, amplitude versus energy. To resolve this mystery, we must first clear up a massive, widespread error. Wave superposition is the superposition of wave field amplitudes, which are complex vectors, not the superposition of energies. Yet, many mainstream scientists, including reviewers and editors of prestigious SCI physical journals, frequently make the childish mistake of treating wave superposition as a direct, scalar addition of beam energies. They assume that if an individual beam has a high amplitude, it must independently carry a massive amount of isolated energy. But physics tells us otherwise. You cannot calculate the energy of a sub-beam simply by squaring its isolated amplitude. The energy flow depends on the impedance of the medium it propagates through, and the phase relationship with overlapping waves. When F1 and R2 exhibit large amplitudes, they are part of a coupled wave network where phase cancellation and impedance differences govern the actual distribution of power. Scene 3, the rigorous rigor of complex energy conservation. In our paper published in Materials Chemistry and Physics in 2022, we provided the first rigorous, mathematical proof of energy conservation at interfaces when the material characteristic impedance, Zm, is a complex number, which is always the case for microwave-absorbing materials. Look at our formula 14 and 14-foot. When Zm is a complex number, the reflected and transmitted energy terms are also expressed as complex numbers. Under the laws of physics, the sum of their real parts, representing the actual active power, is always exactly equal to 1. Energy is perfectly conserved. But look closely at Figure 3 and Figure 4 of our paper. They reveal a deeper physical reality, the critical contribution of the imaginary parts in Equation 14 to overall energy conservation. True wave-based energy conservation is a comprehensive synthesis of both real and imaginary parts. Attempting to evaluate conservation by looking solely at the real part or solely at the absolute values, as mistakenly done in Equation 14', is physically incorrect and mathematically invalid. This sophisticated treatment is entirely missing from prior literature, yet our derivation is completely self-consistent and mathematically solid. It is this unwavering confidence in our logical consistency that allows us to stand firm without needing to seek validation from flawed mainstream textbooks. As shown in Formula 14', the sum of their absolute values is not equal to 1. In fact, because of the phase shifts, the real part of the transmitted energy, Pf1 over pi, can be significantly greater than 1, while the real part of the reflected energy, Pr1 over pi, becomes negative. This negative real part signifies that energy is being stored and returned back through the interface, acting in perfect harmony to balance the total energy equation. This beautiful, exact balance is plotted in our papers Figure 3 and Figure 4, proving that energy conservation behaves fundamentally differently when Zm is a complex variable rather than a simple real number. Scene 4, Conclusion, Cleaning the Swamp of Academic Errors. The lesson of our energy conservation paper is simple yet profound. A thin film is not a simple block of material, it is a wave-interfering boundary device. By deconstructing the amplitude paradox, we have exposed how a failure to understand basic wave mechanics and complex variable functions has led mainstream materials scientists into half a century of erroneous calculations and flawed theories, such as the impedance matching theory. True science is built on rigorous logic and the unyielding laws of conservation. It does not bend to consensus, nor does it tolerate the sloppy mathematics of high-impact journal papers. We invite you to read part 1 of our energy conservation series on Substack or via the link below, and join us in restoring mathematical and physical integrity to modern science. Thank you for watching.